Hello and welcome. Today we're looking at how to determine the hybridization of organic structures, and this is presented by Science Visualized. When you talk about hybridization, basically we're going to be looking at SP, SP2, and SP3 hybridization. This results from the mixing of atomic orbitals. For example, SP will involve mixing of S and P orbitals, so it has 50% S character and 50% P character. SP2 has 1s and 2p orbitals. Remember, we have 3p orbitals, so px, py, and pz. So that means there is 1p that's not used in SP2. In SP, there is 2 p's that are not used, while in SP3, we use all the p orbitals, px, py, and pz, and the s. So in SP2, you have about that 3% s character and about 66% P character. While in SP3, we have about 25%, so a quarter S character and 75% P character. So we see that the percentage of S character increases as you go towards SP. And that means SP will be more acidic. So for example, if you have something that has a triple bond like that, it's much easier to lose that hydrogen. So it's a more acidic structure than, say, a double bond without hydrogen, or even a single bond without hydrogen. So we'll say this is the most acidic, then followed by that, and this will be the least acidic, because this has the least S character, while the triple bond carbon-hydrogen has the most S character. So generally speaking, anytime you see a triple bond, then that means you have an SP hybrid orbital. Anytime you see a double bond, then that will imply SP2. And anytime you see single bond, no double or triple bond, then that will be SP3. Now if we apply those rules, we'll see that this carbon here has a triple bond, and therefore that's an SP carbon. This other carbon also has a triple bond, so that will also be an SP carbon. If you look at the next structure, this carbon has 1, 2, 3, and we're not showing one hydrogen, so it basically has 4 things connected to it, no double bond or triple bond, and that makes it SP3. Next, this carbon has a double bond, and therefore it's SP2. Same thing with this, has a double bond, that's also SP2. That also has a double bond, makes it SP2. If you look at this carbon here, that's a CH3, because we're only showing one bond, meaning that we're not showing 3 hydrogens, and therefore it will be SP3, because it has only single bonds, and carbon is connected to 4 different things. This oxygen here has 1, 2 bonds, but also has 2 electron pairs. So each pair is considered an atom. So basically you have 1, 2 bonds and 2 pairs, so that makes 4 things, and therefore that will be SP3, and that's why water is SP3. That hydrogen there is SP3. This carbon has 3 bonds and a hydrogen that's not being shown, and therefore it's SP3. This oxygen, similar to the one we saw before, has 2 electron pairs and 2 bonds, making it SP3. This oxygen has 2 lone pairs and a double bond. Because it has a double bond, that will make it SP2. Just for the sake of argument, this hydrogen does not have a hybrid orbital, so that basically just has S. Remember, it has 1 electron, so the electronic configuration is 1s1, so that just means it has an S orbital. So that means this bond here involves an overlap of sp3 orbital, which is tetrahedral, sp3, overlap with an s orbital, and that one s orbital is the one for hydrogen, and then the sp3 is for oxygen. Then you have the lone pair of electrons on the oxygen, and then you have the other side connected to the double bond carbon, this one here. Thank you.